My dear students, welcome to Easy BTech, your guide for BTech and beyond. We are discussing about signals and systems subject, and today's topic we are going to discuss is relation between rise time and bandwidth. So very important topic for examination. And before going to discuss our topic, all of you subscribe, share the channel. This channel is very helpful to you to understand all the BTech subjects easily. So please subscribe, share the channel. Let's start our today's topic, relation between rise time and bandwidth. So before going to that relation, we just discuss what is signal bandwidth, what is system bandwidth. So first we discuss signal bandwidth. Signal bandwidth. So what is the meaning of signal bandwidth? That we can discuss now. Okay. What is a signal bandwidth? So generally consider a continuous time signal x of t. We are taking a continuous time signal x of t, and we are going to apply Fourier transform of this x of t. That will be represented as x of omega. Okay, if you plot it, if you draw this x of omega, that plot we call as spectrum of x of t. We call as spectrum of x of t. Of x of t, and which is this spectrum is minus infinite to plus infinity. The spectrum is extended from minus infinite to plus infinity. So first what we are doing, we have taken a continuous time signal, we applied Fourier transform, capital X of omega. This capital X of omega we can plot with respect to frequency, magnitude of x of omega with frequency, that is called spectrum of x of t. So generally this spectrum extends from minus infinite to plus infinity, minus infinite to plus infinity. Now signal bandwidth means range of frequency or range of frequencies over which 95% of signal energy, 95% of or most of the signal energy available or is there. So range of frequencies over which 95% of signal energy is available. So range of frequencies over which 95% of signal energy is available. So that frequency range is called as signal bandwidth. So where to where most of the signal energy is there, what frequency to what frequency most of the signal energy is there, that range is called signal bandwidth. That range is called signal bandwidth. Okay, so that is a signal bandwidth meaning. Suppose I will give you some examples. If you take voice signal, human voice signal, so the frequency range is 300 Hz to 3.4 kilohertz, that is 3400 Hz. Okay, so 300 Hz to 3.4 kilohertz or 3400 Hz. So in this range most of the signal energy available. So this range is bandwidth. So now if you see bandwidth of voice signal, bandwidth is equal to, this is a 3400 minus 300, that is 3100 Hz. Okay, this is the example how to see bandwidth of a signal, right? Next, another example, music. Music is also a signal. So generally the music range is 20 Hz to audio frequency range 15 kHz. 20 Hz to 15 kHz. Now you want to know the bandwidth of music, that is 15 kHz minus 20 Hz, approximately same 15 kHz. Approximately 15 kHz. And if you take video signal, so the frequency range of video signal is 0 Hz to 5 megahertz. 0 Hz to 5 megahertz. So the bandwidth of video signal is 5 megahertz. The video signal is 5 megahertz bandwidth. Understand? So very simple. So where to where the signal energy is available, what frequency to what frequency, that range is called bandwidth of the signal, right? Clear? Next, system bandwidth. Next thing, system bandwidth. So we are going to define now system bandwidth. System bandwidth. System bandwidth. So if you see the definition, we can understand system bandwidth. For example, I am considering the system gain function or transfer function. I am considering system transfer function or magnitude plot of the system, magnitude response or magnitude plot of the system. It is like, this is the magnitude plot. This is the magnitude plot of the system. So the y-axis is magnitude of the system, h of omega, and x-axis is frequency. This is 0. So here I am taking this frequency is omega 1. This frequency is omega 1. This frequency is omega 1 and this frequency is omega 2. So if you observe the magnitude plot or gain plot or magnitude response, this is magnitude response. Magnitude response. So the magnitude of the system is constant from omega 1 to omega 2, right or not? So the range of frequencies over which the magnitude is or system gain is constant, magnitude or gain is constant, that frequency range is called bandwidth of the system. So where to where our magnitude is constant or gain is constant, that frequency range is called bandwidth of the system. That frequency range is called bandwidth. For example, the maximum gain is 1. For example, the maximum gain is 1. At omega equal to omega 1, the gain value 1 by root 2 into 1. 1 by root 2 times of maximum value, that is 1 by root into 1, 1 by root 2. And omega equal to omega 2 also, the gain is 1 by root 2 times of maximum value, 1 by root 2 into 1, 1 by root 2. Right? So these are called cutoff frequencies, omega 1 and omega 2. Now the bandwidth definition is range of frequencies over which range of frequencies over which range of frequencies over which gain of the system is constant. Gain of the system is constant. So where to where the gain is constant. That frequency range is called as bandwidth of the system. So from the graph we can write bandwidth of the system is equal to omega 2 minus omega 1. So here omega 2 is called cutoff frequency, higher cutoff frequency. Clearly it is higher cutoff frequency, and omega 1 is lower cutoff frequency. This is lower cutoff frequency. So this is the bandwidth of the system. Okay, by this plot we can understand well. Omega 1 to omega 2, the magnitude is constant, almost constant. That frequency range is bandwidth of the system. Let's go to now topic relation between rise time and bandwidth. Relation between rise time and bandwidth. Rise time and bandwidth. So for this I am going to consider a system RC low pass circuit, relation between rise time and bandwidth. So we are considering RC low pass circuit. This is RC low pass circuit. So input signal Vi, voltage, input voltage Vi, output voltage V0, and we know the transfer function of this RC low pass. The transfer function we know, we derived in the previous session. So this circuit or this system is RC low pass circuit. Now the transfer function of this RC low pass is h of omega. Transfer function is represented as h of omega is equal to V0 of omega by Vi of omega, which is equal to 1 by 1 plus j omega RC. This we have seen in the previous session, so that is why I am writing directly 1 by 1 plus j omega RC. So this I am going to write 1 by, so I am going to take common RC in the denominator. So here you get 1 by RC plus j omega, 1 by RC plus j omega after RC is common. So this RC we can write in the numerator. So h of omega is equal to 1 by RC divided by 1 by RC plus j omega. Is it right? Now I am going to apply inverse Fourier transform. Apply inverse Fourier transform. Inverse Fourier transform. So inverse Fourier transform of capital H omega is equal to inverse Fourier transform of 1 by RC divided by 1 by RC plus j omega. Okay, so already we know that Fourier transform of e power minus at u of t. What is the Fourier transform of e power minus at u of t? 1 by a plus j omega. So our now inverse Fourier transform of 1 by a plus j omega will become e power minus at u of t. Okay, 1 by a plus j omega inverse Fourier transform will become e power minus at u of t. Fourier inverse will become, or inverse Fourier transform will become, right? So our situation also same like 1 by a plus j omega. So that is why here I have taken common RC, because we know 1 by a plus j omega inverse e power minus at u of t. So I converted the h of omega like 1 by a plus j omega. So by that we can write 1 by RC in the numerator, 1 by RC, it is same, and e power minus at u of t. In the place of a we have 1 by RC. So e power minus 1 by RC t, AT, u of t. So this is the h of t, impulse response of the system. What we call h of t? Impulse response of the given system. So here we have given system is RC low pass circuit. Its impulse response we got, how much we got? 1 by RC into e to the power minus 1 by RC e to the power minus 1 by RC t u of t. Okay. So this is the impulse response of the system. Now I am going to apply step input. The step signal we are applying now, u of t, unit step function or unit step signal. So output I am taking as y of t, for example v naught, which will be y or y of t. So input is x of t, this will be u of t, unit step function, output is y of t. So I am going to see what is y of t. Just I am going to derive y of t, right? So let's take LTI system. So input is x of t, input is x of t. This is a LTI system. The input is x of t and output is y of t, and impulse response is h of t. So in the place of x of t we have u of t. So in general the output of the linear system is, we know output of linear system y is equal to, or y of t equal to x of t convolution h of t, right or not? So in the place of x of t we are taking u of t, okay, and in the place of h of t already we know 1 by RC e to the power minus 1 by RC t u of t. So here both are causal signals. Input is a causal signal, h of t is also a causal signal. Therefore the convolution integral, so generally the convolution is from minus infinite plus infinite, x of tau, h of t minus tau, d tau. Okay. So now here x of t is a causal signal, h of t also causal signal. Therefore the limits will become 0 to t, not from minus infinite to plus infinite. This is the reason, this already we discussed. So here x of tau, h of t minus tau, d tau. Limits are changing because of both are causal signals, x of t and h of t. Let's go to this integral now. Y is equal integral 0 to t u of tau, right, x of tau, that is u of tau, h of t minus tau, that means 1 by RC e to the power minus 1 by RC into t minus tau, and u of t minus tau, d tau. So these two we substituted. First one is x of tau, second one is h of t minus tau. So here u of tau 0 to t 1 and u of t minus 1 also 1. These values are 1. Therefore this integral is 0 to t, 1 by RC we can write outside, and e to the power minus 1 by RC t minus tau d tau. So integration is with respect to tau. So keep tau is inside the integral. Y of t equal to 1 by RC and e to the power, we can write this e power minus t by RC outside the integral because it is not tau. So e power minus t by RC and integral 0 to t e to the power minus and minus plus tau by RC d tau. So integration of exponential is exponential. Now 1 by RC e to the power minus t by RC, and integration of this exponential is e power tau by RC, and limits is from 0 to t. So apply upper and lower limits, just simplification mathematically. So y of t will become 1 by RC e to the power minus t by RC, upper limit here plus t, so t by RC e power, and lower limit is 0, e power 0 will become 1. Right? Now we can multiply this inside, e power minus t by RC, e power plus t by RC. So after multiplication, this will be the result. 1 minus e to the power minus t by RC into u of t. We can write into u of t because this answer is right sided answer, 0 to t, 0 after. So u of t value is 1, 0 after. Right? So we can write into u of t. So this is a output y of t for the taken system, for the given system. Okay? And if you plot it, I am going to plot it 1 by RC. So y of t expression we have 1 by RC into 1 minus e to the power minus t by RC u of t. So if you plot it, if you plot this, so here x-axis is time and y-axis is y of t. So if you take t value 0, here e power minus t, 1 minus 1, 0. Right? And if you take t value infinity, e power minus infinity, e power minus infinity. So here integration e power minus tau by RC, again 1 by RC we get, because it is integration here. So here I forgot to write that. Again 1 by RC we get. Here also again 1 by RC. Right? So 1 by RC get cancelled. This will not come, 1 by RC will not come. Now here also 1 by RC will not be there. Right? So if you take t value 0, 1 minus 1, 0 starts from 0, the y of t starts from 0, and if you take t is infinity, e power minus infinity is 1, sorry, e power minus infinity is 0, so 1 minus 0 is 1. So y of t will go to 1 from 0, it reaches to 1 as t goes to infinity. So this is the plot we get, and this is the y of t expression. Okay, now I am going to define rise time. What is a rise time? So at t is equal to t1, the output is 10% of final value, means 0.1. At what time? t1. And at t is equal to t2, at t is equal to t2, output is 90% of final value. What is the final value? T is infinity, y of t is 1. So 1 is the final value. 90% of final value, that is 0.9. So this interval t1 to t2 is called rise time. We indicate as t suffix r. This is the rise time clarity. So time taken by the response of the system to rise or to increase from 10% to 90% of final value. That is the definition of rise time. So I am writing now. Rise time is, what is the rise time? Time taken by the response of the system, time taken by the response of the system to rise from 10% to 90% of, to rise from 10% to 90% of its final value. So how much time it is taking from 10% to 90% of its final value? That time is called rise time. So from the graph, rise time can be written as T2 minus T1. So we need to calculate T1, we need to calculate T2, then T2 minus T1 will give you rise time. So that I am going to do now. So at T is equal to T1, y of t value is becoming how much? 0.1. So this concept we are going to keep in y of t. So now y of t, which is the 0.1, is equal to 1 minus e to the power minus t1 by rc. Okay, just simplify this. E to the power minus t1 by rc is equal to 0.9, right? E to the power minus t1 by rc equal to 0.9. So just keep it as 1. And similarly at t is equal to t2, at a time interval t2, y of t value. So see the graph in output y of t. What is y of t value at a t is equal to t2? 0.9. So 0.9. This we are going to substitute in y of t. So 0.9 is equal to 1 minus e to the power minus t2 by rc. By this we can get e to the power minus t2 by rc will become 0.1. This is the 2. So we are going to do 1 by 2. E power minus t1 by rc is 0.9, e power minus t2 by rc is 0.1. So let's do 1 by 2, that is e power minus t1 by rc divided by e to the power minus t2 by rc is equal to 0.9 by 0.1. So we are just simplifying it, right? Now this will become e to the power minus t1 by rc, right, and plus t2 by rc. So powers are added, okay, is equal to 9. Now we can take common, e to the power 1 by rc is common, then we get t2 minus t1, t2 minus t1 is equal to 9. Now here we are going to apply natural logarithm because we have exponential. To remove that exponential, both sides apply natural log. So log, right, and e to the power 1 by rc t2 minus t1 is equal to log 9. So log ln natural log means base is e. So here base e and e 1, then 1 by rc t2 minus t1 is equal to log 9. So log 9 value is the value of log 9. Its value is 2.2. 2.2. From this t2 minus t1 is equal to 2.2 rc. So this is the rise time tr. 2.2 rc we got, right? This is about rise time tr. So how we got it? We have taken output y of t, we have seen t2, t1, then t2 minus t1 is 2.2 rc. Now we are going to see bandwidth. So bandwidth of the system. This will be obtained from magnitude response or frequency response, bandwidth. So already we know for the taken system, this is the magnitude response. X-axis is omega and y-axis is magnitude of h of omega. It starts from 1. At frequency omega c, or fc, which is equal to 1 by 2 pi rc. Already we know this. So where the magnitude is constant, 0 to omega c, the magnitude is constant. Therefore, this range will be bandwidth of the system. This range is bandwidth of the system. So here I am representing bandwidth 0 to omega c or fc. And which is fc? What is fc? 1 by 2 pi rc. This already we know. In the previous session we discussed already. So now the bandwidth of the system is 1 by 2 pi rc. 1 by 2 pi rc. And we know rise time and we know bandwidth. So these two we are going to, by seeing these two, we are going to write the relation. We are going to write the relation. So now in the place of RC we can write 2 pi into bandwidth. Right or not? We can write 2 pi into bandwidth. So just I am going to write the relation, nothing else. So here from this you take RC. RC will become rise time by 2.2. So this RC I am going to substitute in the bandwidth. Now bandwidth will become. So this is RC, here we have 1 by RC. So you can write 1 by RC. What is 1 by RC? 2.2 by rise time. So this 1 by RC I am going to write 2.2 RC. Okay, 2.2 not RC, 2.2 by rise time. So 2.2 by rise time, and again we have, this is only 1 by RC. Again we have by 2 pi. So by 2 pi. So this is the relation, and here 2.2 and 2 pi, this value will become, after division 2.2 and 2 pi, this value will become 0.35. 0.35 by rise time TR. So in the denominator TR is there, that is as usual. So this is the final relation between rise time and bandwidth. So I am writing bandwidth is equal to 0.35 divided by rise time, or bandwidth into rise time is equal to constant 0.35. And finally, if you observe the relation, if bandwidth is more, rise time is small. Rise time is small, means system is fast. This is the point. Rise time is small means system is fast. Right or not? And we can speak reversely also. If bandwidth is less, rise time is more, and the system is slow. System is slow. So how we are saying it? Because the relation says that bandwidth is equal to 0.35 by rise time. So bandwidth is inversely proportional to rise time. Bandwidth is more, rise time is small. Bandwidth is less, rise time is more. And the product of rise time and bandwidth is constant. This is also point. Product of rise time and bandwidth of the system is constant. This is the final conclusion. Okay, so students, please watch videos regularly. Thank you students.